Thank you, Maria Jesus. Hi, everybody, and welcome to this session, which will be like a workshop. Today, we'll see how to build our first end-to-end machine learning project. So we'll build a model and we'll take it to production and do some predictions with it. To start with, I think that I would like to give you some motivation. So most of you, if you never built a model, a machine learning model, probably ask yourself a question, do I really need a model? And my question for you would be, well, do you make decisions? Because if you do, chances are that you need to do this kind of data-based decisions. And to do that, you need to do models. And this kind of thing happens all the time without you noticing it. In your email account, when you look your mail, in your mobile maybe, what happens behind the scenes is that a new mail arrives and there's a model which is able to label it as this mail being spam maybe, with a percentage of confidence for that prediction. And based on that percentage of confidence, the mail gets sent to one folder or another. In this case, it gets sent to the spam folder, because we decide that all mails that have this label and have a good enough level of confidence should go to that folder. The same happens when you buy something maybe with your card. There's a model behind the scenes that is looking for the different properties of this transaction. And if it's suspicious, then it assigns a number, a score, that tells us how anomalous that transaction is. For anomalous transactions, we decide to do something and tag them as fraud. Maybe someone specialist would have a look at them and decide which are the actions to take from that. In order to be able to do that, you need to learn to build a machine learning project. So the challenge today will be having some data, which is published in Kaggle, and trying to build our first machine learning model using that data. In this case, the project that we're going to do today is based on a data that describes some credit loans. It's called, the contest in Kaggle, it's called Give Me Some Credit. And the idea is trying to find out which kind of people did or did not pay their loans. You can access this information in Kaggle. As I said, you see that URL here at the bottom. And finally, what I would like to do based on that data is trying to minimize the investment risk I have by predicting these people that is defaulting. The first step to do that would be defining the question, right? And here's my homage to Monty Python. But the idea is that you need to phrase whatever you like to find in the most detailed way you can. So whenever you have posed the question, then you should ask yourself, is that really all there is to it, what I want to find? Because sometimes explaining what you want to find, it's not so easy. An example would be if you're looking for a customer which is in default, what are you looking for, really? Your data will probably not have a field that will tell you whether a customer is in default or not. What your data will have will be some data, one row per customer, and the payments that customer has been doing 3 months ago, 2 months ago, 1 month ago, as you can see here in the columns. And the idea is a customer in default when he misses some payments? That's the scenario we're looking for. Or is the customer considered to be in default when she pays late? Maybe one of those conditions are the key for you to define a customer in default. Finally, the idea behind that question is, what's the maximum delinquency that we as a business are allowing? So try to think about that. It takes some time to reflect what's the real condition that it's causing the objective that we're going to predict, the thing that we're going to predict. In this case, the contest itself defined the question, right? And I told us, well, our idea, our goal is trying to predict who will be 90 days past due or worse. And we would like to act only on them because these are the people that are considered to be in default for us. And that condition is the thing that sets the real tag, the thing that we're going to predict. As you see, by defining this question, we are able to add one new column to our dataset where the default condition is defined. So the first customer, well, the first, the third, and the fourth would not be in default, while the second one would be in default. That's the label, and we've been able to add it to our data just by defining strictly the question that we want to solve. So what now? Well, the first decision that we have to do trying to solve this problem is how to do it. So our recommendation, of course, is choosing one of the best platforms you can have and using BigML. So I'll give you some minutes to join the platform. You see that you can register and there's this form here that you can fill in with your name, your email, the username that you choose, and the password that you prefer. And use also the BigML school code if you want to redeem a voucher here for special conditions like a pro account that will help you, will let you use 4 GB data sets, and also you will be allowed to run 8 parallel tasks at once. The form is in this URL you see here at the bottom, bigml.com/accounts/register. And by filling it, you'll become enrolled in BigML if you haven't so far. And now, while you are doing this registration, I can describe what kind of data are we going to work with. In fact, when you use data and you receive data, it's not only about the actual content of the files that you get, it's also about knowing what this information means. And to that end, we need a kind of data dictionary. So we need to define which are the things that are stored in that file. In this case here, you can see that we have several variables on the left and the description for each of them. And to determine who is 90 days past or worse, their due, the key field in this case is the serious delinquency in 2 years, the field, because it's described as such, as the person who experienced 90 days past due delinquency or worse. Yeah, and you see that the contents of this file would be a kind of label, yes or no. This is the objective field, the thing that we'd like to predict. And what are the rest of fields? The fields that could be related to that information, to the fact of a person being a serious delinquent in 2 years. Well, the rest of information that is in our data. So as you see, we are provided with information about the revolving utilization of unsecured lines, or the age of the customer, or the number of times that he has been 30 to 59 days past due, or the debt ratio. So information about the financial situation of that person, finally. Once we know what kind of information we have, we should look at the real data, right? And the real data is nothing else than a CSV. So it's numbers or text separated by commas. That's the only thing that will be uploaded, that will be used by the model, the algorithm, to find the model for us. This is stored in the original context as a file, which is called CS training, and that's what we're going to use today to start building our first end-to-end project. So the first thing we'll do is, of course, uploading this data. Let's go to BigML. I can just open the file selector and I will get it from it. But you should also be able to drag and drop it. It took some time, so I prefer to open it from the selector. And once I upload this file in BigML, what will happen? Of course, as I said, I'm just uploading some numbers and text to the platform. And the first thing that the platform needs to know is, what does this file contain? And that means interpreting how the data should be used in the algorithm, which means finding out which are the field types assigned to every different column in your data, for instance. And also, which is the locale. So if you have numeric data, which is the decimal separator that is going to define correctly the contents of your data. Or maybe you have some missing information, and that missing information in some of your rows might be defined by having some text. Maybe you have a null or an I text that will just stand there to show you that the information is not really recorded for that row. This kind of tokens should be also defined so that the algorithm interprets correctly the contents of your data. Or maybe you have also text fields or items fields. And of course, the contents of these fields are composed. I mean, the original, the algorithm will not really interpret the entire field, but the components of it. If you have a text, it will probably need to parse all the different words and act based on the frequency of each of the words in each row in your data set. So this kind of parsing is the way of telling BigML what's the real content that should be used by the algorithm to find the patterns that will lead to our predictions, right? And that's the data dictionary that the source is learning from your data. If we go back to the platform, we can open this new object that has been created, this new source, and you'll see that what BigML, the platform, has inferred is that the first line in your dataset contained the name of the different fields that you provided. And therefore, it has used these names to name also the fields in the source. So it started understanding the structure of your file. And the second thing it inferred is that the nature, the type of the different fields, the information that you provided. The platform has looked at the first instances in your data set. You see here in columns the first instance, the first row in your data, the second row in your data, and the third row in your data. And based on the contents of that, it has decided that the first field seems to be a numeric field, right? This is the ID, so a unique identifier for each of the rows. And based on that, the idea is that the type of the field should be set to numeric. While the second one, which is the field that we're interested in predicting, the serious delinquency in 2 years, is tagged as a categorical field. And that's because the contents of this field are only ones or zeros. So as there's only 2 categories in this field, the tag has been assigned, the field has been assigned a type, which is categorical. The rest of fields, as you see, have been also tagged as numeric, and that's pretty convenient because the first rows were containing this kind of information. Of course, we could be wrong. I mean, maybe this field has only zeros or ones, but it's still a number, right? Not a code. If we are, we always have the chance to configure this source differently. We could here change the type of the field to the one that we know it's correct, right? And we can also configure other things like the locale that I mentioned before, or how you analyze the text that you provide in any of the text fields or the items fields or the missing tokens, all these elements that define how the source information, the data that you provided, will be parsed for the algorithm to consume, right? In this case, well, we did a pretty good job just by dragging and dropping here. So the next thing that we need to do is trying to find out the real content of all the entire data set, of all the entire file that you provided. And that's done here using this action, this menu icon that you see that has a cloud and a thunder on top of it. You see the direct actions that you could do in just one click. And the first one is the one-click dataset. We just had the data dictionary. Now we want to see the real distribution of all the data that we just uploaded. And we do so by clicking here and letting the dataset build. What's the dataset going to tell us then? Well, the dataset is going to tell us how is data distributed. So what we're going to obtain is, by analyzing the entire dataset, is the histograms that will tell us how the values are distributed in the entire range of the numbers that the field contain, if it's a numeric field, or in the categories that the field contains, if it's a categorical field. Will also tell us statistics as to which is the minimum, the maximum, or the mean. Will also tell us whether there were missings in our data, so whether there were values that were not informed, and also the number of errors that we can find. Maybe we can have errors because we defined a field to be a number, but their contents are not really only numbers. Some rows have other content, or maybe you have a datetime and the format of the datetime is not correct, or instead of a datetime you have a text. So these kind of errors will also be reflected in the dataset information. And by just changing to here, we can see that the dataset has been built, and the information for us in this case is that we can see the count of rows that we had originally in the file that we uploaded. It's 150,000 rows. And we also see that some of them have missing information in the monthly income. So 29,731 of the rows don't have the information about the monthly income of the customer. We don't see any errors so far. And we can have a look at the different histograms that we have. Maybe each histogram is some interesting information. You see that there are some instances of people that are between 0 and 22.73. So it's people below, with ages below 22, 73, so 22 in this case, nearly 23. And you see that the higher ages are between 106 and 109, which of course it's great for them. We all would like to get there. And here are the statistics of the field. So you can see that the minimum has been set to 0. So maybe some instances, instead of some instances did not have the information about the age of the customer, and instead of putting there some text to indicate that, they just filled in the field with a 0. That's something that can happen and should be addressed, of course. And there's a maximum of 109, as I was saying, and you also have information about the mean or the standard deviation. So it gives you an idea of how the data was distributed in this field. You see that all the different fields that you have here are numeric fields, so the distributions are similar. But for the serious delinquency in 2 years field, that is a categorical, and of course contains only 2 categories. The category that defines the people that paid their loans, so the zeros, which is the majority of people, and it's 139,974 cases. And the minority of people, the small amount of people that did not pay their loans, so they were serious delinquent in 2 years. And that's just labeled with a 1 in this field, right? So that's the minority of the instances that we have. You also can notice that there's this mark here, this red mark, which is telling you that this field is not preferred. This mark appears in BigML when we find out fields that contain unique values, like in this case. An identifier is just a field that is assigned at random to every row that comes into the file, just to make sure that there can be identified. So they are unique. And in this case, a field that contains unique values is not useful for the algorithm to just group in different groups, to split the data into categories, because it cannot be used. I mean, it has no relation whatsoever with the fact that someone is a serious delinquent, of course, because it's assigned at random, and also it cannot be used to group the instances together if you want to classify them. So these kind of fields are useless for the algorithm, and we mark them to be so. It's the same case if you have a constant field. If you have a constant field, you cannot use the field to split also the data. So it will also become useless, and we would mark it with this exclamation mark, right? So in this case, these fields that are marked as non-preferred will not be used by default when you build your models. Of course, you can choose to do that. And if you see there's a pencil here, this icon where you can just click and change the type, whether this field is preferred or is not preferred, to include it in your models if you choose to do so by some reason. And here, let me also change something. This is the field that is considered to be the target of our model. So the thing that we want to predict, the objective field in our language. By default, BigML considers that the last field in your data set should be the thing that you wanted to predict. But in this case, of course, that's not the case. We want to predict serious delinquency into years. So let me change it here for you. And thus, it will be associated to the data set, meaning that whenever I create a new model from that data set, the default will be trying to predict the serious delinquency in 2 years. If I want to predict another kind of thing, another kind of field, I can, but then I should just configure my model to do so. So now I'm ready. I've seen the statistics so far. So I've not yet done anything that has a relation with the machine learning world, really. And now I'm going to do that. I'm going to create a model. The idea to create a model is that I need to extract insights from this information that I have, right? And what kind of insights will the model extract? Well, let's see it in motion. Let's just go to the platform and create one model. Again, we have this action menu that allows us to create different kinds of models. You have maybe unsupervised models here on the right and supervised models here on the left. And in this case, I will create a supervised model because this kind of problem that I have today, it's a classification problem. And when I have a classification problem and my data set has a field that contains the label of that thing that we want to predict correctly placed for a collection of examples, as is the case, then the kind of problem that I'm addressing is a supervised machine learning problem. And I could choose to use any of these different algorithms here that will build models for me, right? But the first one here is the one that will give me more insights. So I'll choose to do that. It's a decision tree model here. I'm starting creating the decision tree, and let me see which kind of information will it provide for me. In fact, it will provide the patterns that the data contains. So which kind of conditions allows me to say that someone will pay or not their credits. So this kind of information will appear here on the right when we build the model, and are sets of conditions that are fulfilled by subgroups of the people, of the examples that I just provided the algorithm with to learn from. That define whether these people that fall into this group of conditions finally don't pay their loans, or finally are delinquents or are not. This kind of patterns is the information that the model contains. Also, it will provide for me another kind of information. So which are the fields that are more important into separating this data and classifying it in different groups. We'll see how this is extracted from the tree. We'll discuss that. And also we'll have other kinds of things like predictions and so on, right? But let me see how that works in the platform itself, or this example we're building today. This is how the model that we just built looks. That's a decision tree model, and the name is related to the fact that if you look at this picture, you can figure that as a tree if you look at it upside down, right? So this would be the root of the tree. And that means that here at this node, you have all the different examples that you provided the algorithm to learn from. You see that here are the initial 150,000 instances in my data set and separated in the two classes, right? You see here the people that paid their loans and the people that didn't, right? And here you can see that the green nodes, which are the leaves of my tree. And these leaves is where people is classified into one of the categories, into being people that pay their loans or people that don't. So I don't have more questions to do. When I'm here and I don't know anything about my customer, the first thing that the model would tell me is that there's a high confidence that this customer will pay his or her loans, right? Because mostly people do pay their loans. That's the first thing that the model predicts with no information about the person that comes to you and asks for a loan. But what happens if I just make a question? You see on the right, there's a question telling me, ask about the number of times this person has been 90 days late. Well, maybe if I ask about that and I have more information and I know that this person has never been 90 days late, well, I will have a higher confidence that this person will pay his loans, because you see that here the percentage has increased, right? There's more people that pay their loans against the people that didn't. But if I just go through the other branch of this tree and look at the people that had been, sometimes have been a number of times 90 days late, then I see that the proportions, they're yet about paying their loans. I mean, the majority still pays their loans, but the proportions are more balanced. There's nearly the same amount of people that pays their loans against the people that doesn't. So that confidence about people paying their loans is not so great here. And if I go on and keep asking questions, maybe I would ask whether this number is exactly 1. So did just be 1 times 90 days late, and then they didn't use revolving utilization of unsecured lines, then I would have a response. And that's people that mostly will pay their loans. And I have a confidence of 80% here. Okay, and they are mostly into paying their loans. You see that I've reached a green node. It means that I have no more questions that can help me separate the people that pay their loans from the people that don't pay their loans at this level. So the final prediction of the model here would be, with this information, I can only tell you that with the data that I have seen for training, I'm pretty sure that these people will pay their loans. But what if, as it is the case, what I'm interested really is in the people that don't pay their loans? Which are the patterns that define this kind of users, this kind of customers? Well, I can just filter here to see the patterns appear. And these are the patterns for the people that don't pay their loans. I can go to any of these nodes that ends up in a group of people, the majority of them not paying their loans, and see which are the conditions that led to that result for that group of people. So here, for instance, there's people that have been repeatedly a number of times 90 days late, and they never had been a number of times 30 to 59 days past also late. But here, the number of times they have been 90 days late is bigger than 2. So if they have been so repeatedly 90 days late, it's probable that finally they end up not paying their loans. That's the kind of pattern that we can extract from that group of people. But as you see, there's not only a pattern, there are several of them. Each of these branches that lead to a green node is telling you a different pattern for the people that finally don't pay their loans. And the entire tree is just providing also an information about which are the conditions, the fields that are really important to determine if people will pay or not. So here, using this model report, you can see which are the percentage of importance of each different field in your data set when you try to classify all throughout the tree all the different people that will pay or not their loans. Here you see that the field that does give you more information about that all throughout the tree, so in every split, in every single pattern that you can obtain, is the revolving utilization of unsecured lines, and with a 23.29%. And the second one would be the number of times the people has been 90 days late, right? And the third one, the number of times they are 30 to 59 days past due, but not worse. And on the other hand, you have the fields that are not so important to determine the different classifications, which maybe are the number of dependents. Having this information could be very important for you and for your business, because imagine that you need to do some kind of expensive procedure to get this information of these fields that are located at the bottom of the importance report. This means that maybe if you get rid of this information, the model will not suffer so much. So your classification will be doable. And maybe that can really be saving a lot of money. So having the idea of which information is important to get to create the models and which would be discardable, so which is not so important, it can help a lot in your business. So now we've seen that there's plenty of information that we've been able to extract from the model. We've seen that we have patterns and that we have the importance of the fields, but we also would like to get the predictions themselves, right? We are building this in order to be able to evaluate the next customer that comes to us and asks for a loan, right? So we need a way of having this kind of prediction, this kind of labels that is useful. And also we'd like to have a confidence associated to these predictions. And finally, even so, if we could, we would like to have some explanations as to why did the model decide that that was the prediction based on the data that it has seen, right? And that's the final end of the project. And that's the thing that you should be able to do. Here, you can obtain that just by using, again, the actions menu and looking for the predict form. Based on this model that we're building, you have here a form that you can fill in and decide, well, in my case, there's someone who has been revolving utilization of unsecured lines, and maybe he has been more times 90 days late. And then as we change the sliders, as you see, the prediction here appears and changes, right? Here we have a serious delinquency in 2 years with 52% confidence. And here, if I change the number, probably the case will change too, right? So this is the last part. Of course, this is an individual prediction, and maybe you need to predict for a lot of people. If you want to do so, you can do it too by using the batch predictions instead of the individual predictions. That's another different option that it's available here. And I will not show because we wouldn't have the time, but the idea is that you would upload your data again, create a data set, and use this action to produce predictions for every single item that you have in your original test data set. So now we've seen that we are able to do these predictions that we needed. If you want explanations, you can also add that by clicking the explanations button in the prediction form. Here, if you go to the prediction form again and create a prediction using this button here, you can obtain the explanations for that case that you're going to predict. So if I click here, I can see the difference in the importance that every single field has had in the prediction of that person that will pay their loan with a 90% probability, 91% probability. So you can obtain a lot of information, as I said, from the model. And that's really end-to-end, because someone could just check in this form the variables, the value of the variables of his new customer, and decide based on that whether he would receive or not a loan, right? But the question remains as to, are these predictions correct? So maybe we should ask ourselves if we have a way of knowing whether the model is doing good predictions, is really just matching the values of what happened really. We are provided with some information, of course, in order to do that, which is the original data set. The original data set we used to create the model contains the label that tells us whether these customers ended up paying or not their loan. So maybe we can take advantage of that in order to check whether the predictions of the model were correct. And indeed we can. We can evaluate the models by doing a first split of the data that we have at the beginning, of the examples that we're provided with, into two different data sets. One is going to be used for training, and it's the one that will contain the majority of data. 80% of the data will be used there. And the other one will be used for testing. And we need to make sure that the instances that are used for testing are never used for training, because otherwise the algorithm would see them and would be able to adapt too much to that. If we did so, if we use the same instances to train and test, then the evaluations would be too optimistic, because the algorithm could learn a lot how to adapt to those instances, but would know nothing about what happens with a new customer that is not identical to one of the customers that were analyzed in the training phase, right? So making sure that the instances of the test dataset are customers different from the instances in the training set. Finally, we're able to produce for the test set predictions using the model, and then check whether the prediction that the model did does match or not the real value that we know that this customer ended up doing. So whether he paid or not his loans, right? And that's what will tell us whether the model is doing good predictions, realistic predictions. Finally, this is summarized in some quantities, in some metrics, and this kind of information is what it's called an evaluation, right? And that's the good way of doing it, making sure that wherever data you use in the test, that data is never used in the training of the model itself, right? So now let's see about the evaluation. Let's do an evaluation in BigML. And here, let's go to the model itself first. Go again to the model view screen, and you'll see that the actions menu again give us the option of evaluating the model. In order to do that evaluation, if you remember that, I was about to skip it, I needed to split my data, right? I had an original data set of 150,000 instances, and I need to split that to achieve 80% of these instances in one training data set and 20% of these instances in a test data set. And we have an option in the menu that allows you to do that. The transformation menu in the datasets view contains an option that it's doing that split, training test split. Here, as you see, by default, we have these quantities, 80% goes for training and 20% goes for testing. These instances will be picked up at random, but we provide a seed, so a text, whatever text you choose, to make sure that the instances that are selected at random this time will be selected at random in the same sequence every time I pick up this seed. And that's important, because that's what makes the instances that are selected at random to go through training be just a complementary part of the instances that are held out in the test dataset. So when I create this training and test dataset, and BigML now is splitting this dataset, this original dataset, into this 80% is selecting instances at random to go in each of them. And I see that I end up in a view that shows me the 80% part, so that I can start training from here. It contains 120,000 instances as expected, and I can use that to repeat my process. I will train the model only on this group of instances, and so I make sure that this model has never seen the instances that are kept in the test dataset I just built. And now that I have my model, I will evaluate this model using this action in the actions menu with the instances that I just held out in the test dataset. You see that it's configured by default here in BigML. If I do that, I just use the model to predict every single instance that was in the test dataset. And you see here that there's some results of this prediction. Let's understand which are the results of this prediction. So the idea is that you have some quantities here that are measuring how well the predictions match the reality. And the first quantity that you usually look at is the accuracy, right? Because people usually think, well, my model, the accuracy finally is the number of times I got right the prediction. So the percentage, of course, over the total. But the idea is if you have a high accuracy, then you're probably doing good. And that's the first thing that I might think. And here I see that I have a 93.8 accuracy. So that looks like it's great. You see that, yeah, that's the result I got. So I think it's great, right? Because it's a very high accuracy. I'm happy with that, okay? Well, in 10 seconds, you'll come to me and you'll tell me, I wish to make a complaint. Because what happens here? I need to go further than the accuracy itself. I need to think about where do the errors come from. So do I have errors similarly in both cases, in people that pay their loans and people that don't pay their loans? And just to put it simpler, imagine a different kind of problem. Imagine that you have a bag and inside of it there are 10 balls. And there are 9 balls that are white and 1 ball that is red. And I would like to have a model to tell me when do I extract a red ball. But I just built in a moment a model that will tell you, you will always extract a white ball. Okay, this model is 90% accurate because 9 out of 10 times you will extract a white ball. But this model is useless to you because you're not interested in the white ball's result. You're interested in the red ball result. And this model I built is doing perfectly well for the white balls, but it's doing nothing. It's completely failing for the red ball. In the case we are seeing today here, it's the same. I mean, I'm interested in one particular class, the class of people that don't pay their loans. And this class, which is what we call the positive class, so the people that have a 1 in the serious delinquency in 2 years field, right? This class is the one that I want my model to predict correctly. But maybe this accuracy that I have is just reflecting that I'm predicting correctly the class that of the people that pays their loans. And that would not be really what I'm interested in. This happens often when the class that I'm interested in is the minority class in my dataset. And that's what's happening here. You remember that there were lots of people that pay their loans and just a few amount of them that didn't pay their loans. So we need to pay attention to the different kind of errors that I'm doing in this case. You see that here, these errors are depicted. This matrix here, which is called the confusion matrix, is just mapping the results of the prediction of the model against the real thing that happened. So here you can see that the real thing is that 27,996 people paid their loans. And from these people, some of them were wrongly predicted as not paying their loans, 273. And on the other hand, the people that didn't pay their loans originally was 2,004, of which 422 were predicted to not pay their loans. Only this small amount of people were correctly predicted, while 1,582 were wrongly predicted to be paying their loans. That's what happened, really. So finally, this great accuracy is not so great for the kind of problem that I'm interested in. I need to look at the different errors. This kind of match, which is people that don't pay their loans and I predicted correctly, is depending on the kind of class that I'm interested in. These colors here are depending on the class that I'm interested in. So here, let me go back to the screen and decide which is my positive class. My positive class in this case is the people that don't pay their loans. And when I look at that, I see that I got only 422 right. That's the true positives. So people that were predicted to be of the positive class, or the class I'm interested in, and they were correctly predicted. And we have another good match, which is the true negatives. You see this green light in light green here. You see that these are the people that did not pay their loans and were predicted actually to do so. Both of them are successes in my model, right? And both of them contribute to this accuracy, this high accuracy that I am seeing. But I'm more interested in the errors. I just did here some errors of people that actually didn't pay their loans, these people here, but my model predicted incorrectly that they were going to pay their loans. These are the false negatives. My model predicted that they were negatives, they were people that were to pay their loans, but that's not true. And that's what's in the bright red, right? And then there's another kind of error. There's the kind of error of people that actually paid their loans, but the model predicted by mistake as people that wouldn't. And these errors are marked here as false positives because the model predicted that they were belonging to the positive class, to the people that didn't pay their loans, and that was not correct. That's the kind of mistakes that we do. In fact, when you have a minority class and you're interested in that class, probably you will need to look at other measures different from accuracy. You will need more to look at recall, precision, or even the harmonic mean of both of them, precision and recall, which is the F measure, or even the phi coefficient, which also is a compensated measure that mixes up the precision and the recall. And so I need to have a clear mind about what's the real objective of the problem I'm trying to do. Always remember the goal. You need to predict who will be 90 days past due or worse. So you need to have in mind the costs of failing because the model will not be perfect. And the model has been proved to fail in two different ways. The idea for us, the important thing for us would be to minimize the cost of those failures. And in order to do so, we should maximize the recall. So I need to find out as many people as possible that don't pay their loans, even if in the process of doing that, I'm just leaving out lots of people that would pay their loans, and I mistakenly predict as people that won't pay their loans. Because it's better to lose that kind of business, because I have lots of people asking loans for me, than to have to lose some of the people that will not pay their loan. That will give you a higher cost for your business, right? So I'm interested in this case in maximizing the recall, in finding out whoever is never going to pay their loan. Okay, so maybe I need to tune the model in order to do that. I need to change a bit how I created the model to achieve a better recall, right? And the first thing that comes to mind for me is that as the percentage of the people that belongs to the class I'm interested in is very low, maybe I can try to balance that somehow. I mean, I can try to give a higher frequency when the model sees an instance that that's an example of these people that don't pay their loan. And when you use the model configuration, you can do that in BigML. Let's go back to the screen to create the model. I can go back to the model using this menu here. And again, when I am in the model, I can go back even to the data set to see the configuration that I used by default. You remember that I created this model in a one-click, and that means that all the parameters that were used to create that model were chosen by default. But I now can choose to change a bit that set of parameters, right? And the thing that I would like to change is the weights that are associated to each of the rows that I'm providing the algorithm with to learn. So here I can choose to have a weights that balance the unbalanced classes that I have in my objective field. And that's done by assigning a frequency, which is the inverse of the proportion of unbalance, right? So the lower the number of instances that go for the class I'm interested in, the higher the frequency I will associate, so that finally the model sees as if they were the same number of instances from one class and the other, right? That's the kind of thing that I'm doing when I change this model parameter. And I create a new model using this technique, using this kind of weight associated to the minority instances, minority class instances. You see that here the balance sign appears because this model is weighted. And that's created a different structure, selected different patterns, of course, for me. And I like to evaluate this new model to see if it does better or not than the previous one. So I go again to evaluate in the actions menu and create a new evaluation that will show me different measures. Okay, now in this case, I choose again the positive class. And I see that, you remember that here, the previous model got right about 422 instances. And in this case, by doing this change in the parameters in the model, I've been able to recover 1,553 instances. So much more instances of the total 2,000 that really didn't pay their loans. That's reflected here. This model has a higher recall than the previous one. On the way, I lost precision. The precision is lower because I predicted more people as not going to pay their loans, which in fact they really paid. So that's a trade-off. If you want to increase the recall, you usually end up lowering the precision. But in this case, to my business, that's not so important because I have lots of people that ask for loans. So I can just refuse to give these people the loans with no impact in my business, right? Or with less impact that I would have if I didn't predict correctly the ones that were not going to pay their loans. So that's a sacrifice I'm willing to make. That's something I can achieve, right? And that's how you need to think about whether a model is good for your business or not. That's how you evaluate the model. You compare the actual errors of the unbalanced model to the ones of the balanced one, and you decide that the balanced model works better for your business because the impact in cost of the balanced one is lower than the impact in cost of the unbalanced one. So you see, you pick up more people that are not going to pay their loans here than here, even if there's more errors for the people that in fact will pay their loans and you tag them as not going to, right? But that's not, that hasn't a high cost in your business in this case. So you see that there's some parameters that we can change, even there's different types of models that we could try. Imagine that you want to try a neural network model to do that. And also there will be lots of coefficients that you can use when creating these neural network models. Should I go one by one and changing all the different parameters that I have? Of course, hopefully not. I mean, that's why platforms are. And we offer that possibility of having an automated procedure for looking for you through the different combinations of models and types of models to see which is the one that will give you the best results for your problem. And that's what OptiML does in BigML, right? If we go back to the original screen, I can just use the data set that I use for training to create an OptiML. So to do in an automated procedure this search for the best type of supervised learning model available for me. Here in the configuration menu, you see that I can configure an OptiML. And the things that you could configure is the maximum time that you will be training, of course, because it will take for a while to create these kind of models, as these are this is an automated procedure that goes on trying to build new models and evaluating them in a smart way, of course, looking for the best ones, using machine learning insight to find the best configurations to be tried. And also you can decide which are the things that you want to optimize. In this case, I was telling you that we're looking for a great recall. So probably what I would do is just asking for optimization of the recall for my positive class, for the class of people that don't pay their loans. And on top of that, I will just analyze maybe models and deep nets in this case, and just getting rid of ensembles or logistic regressions. Deep nets are the neural networks. And also I would select the test data set. So I would ask for the test 20% split that I remember for test. You could do all the choices. And from there, I will create an OptiML. And that starts doing this procedure that it's automated and it's looking for models for you. I will show you one that has already been made because I don't have the time here to wait for the result. But if I go back to another project that I had created previously, I can show you the result of this procedure. And the result for the procedure would be I've built lots of models. Here you see that I built 63 decision trees against 2 deep neural networks. And I've analyzed the recall for all them. And I see that the one that gives us the best recall in this case for this class, for the class of people that won't pay their loans, it's a decision tree. So against the neural network, the decision tree in this case was giving you better results. And that's how it works. I mean, in this case, the winner is a 15 nodes decision tree that is balanced and also pruned, which means that the nodes that have a few instances are removed, right? So not always the neural networks are the best solution. Depending on your data, the type of model that would feel best will be different. You need to try them all. That's why we provide these kind of automated solutions that look throughout the different space of parameters and types of models to provide the best one for your problem, to optimize the measure that you want to optimize, right? Well, we've seen the project itself. I mean, we found the best model and we would put that model into production. You see how BigML works right now, but now I'm going to give you a glimpse of what BigML will be able to do next. And linked to the problem that I just defined at the beginning about the trees, about the large, today we'll be able to see how to solve that using BigML in the next days or months. So here we are showing you a thing that is in beta. I have some images about larch on the right, about trees that are larches, and some images about willows. I just packed them into folders, one for the larches and one for the willows, and uploaded them as a zip file into the new beta of BigML. BigML processes the source and shows you that it has found some images. It knows that there's a file name and it labels them with the name of the folder they are contained in. But of course, you can change that label if you want to, if you wanted to just mend some errors. You could configure the source, of course, and decide which kind of image analysis you're going to make. I just select all the different kinds available and create a data set as we did previously in this session with that information. It's summarizing the different features that it has found in the unstructured information of the image. You see that you can see all the different images that the data set contains. And finally, I would do as I did before in the credit case, I would do a training and test split to evaluate whether the model that I'm going to build is performing right. My idea here would be an automated model that would tell me whether a tree is a larch or a willow. So here I use an ensemble in this case to do that. So an ensemble is just a collection of decision trees. Each of them will vote, and finally the ensemble will summarize that vote. And I can do predictions, of course. I just look for one of the images of the larch. This is a nice larch, you see here, and I'll see whether the model does the prediction correctly. And finally, of course, the ensemble votes, and we end up having a prediction of that tree being a larch. And if I do the same to try with a willow, and I have this nice picture looking like a Monet picture and a Monet build of the willow, then I see that even if it's mixed with other vegetation, finally it finds out that it's a willow. And if I want to evaluate that to see if I'm doing correctly, because the predictions could be right or not, I see that the evaluations are sound enough. I mean, you see that the recall, the precision, and the accuracy, both all three of them are perfectly all right, are very high. So I have a nice model that will tell for me whether to tell apart a larch or not from far, far away, which was the initial question of this workshop. So that's the end of the workshop for today. Thank you very much for your attention, and see you in the next machine learning schools.